Number 11, evaluate the integral of x to the fourth plus x squared over x to the fourth. This is a non-calculator problem. What we are going to do to tackle this one, we can't separate it yet because of the x to the fourth, so I'm actually going to bring the x to the 4 up top. When I do that, I'll have x to the 4 plus x to the second times, not plus, x to the negative 4, and then I'm going to distribute the negative 4 by adding the exponents, so I'll get x to the 0 plus x to the negative 2. X to the 0 is just 1, so I'm going to have 1 plus x to the negative 2. And now since there is just a plus sign, I can go ahead and take the integral of both sides, both parts. The integral of 1 is x, and then plus, if I add 1 to the power, I'll get x to the negative 1, and then the reciprocal of negative 1 would be negative 1. And then just rewriting this, I'll get x minus 1 over x plus c. And that is my answer. That's all there is to it. Number 12, evaluate the integral from 1 to 5 of the absolute value of x minus 3 dx. All right, the biggest thing on this one is just knowing a picture, because I think that's the easiest way to go on this one. Absolute values look like a v. We just need to figure out where it is v'ing. And so here, if you set x minus 3 equal to 0, that would be at x equals 3. So we know that at x equals 3, that's where we're going to have the v going on. So this is what this absolute value is going to look like. We want to take the integral from 1 until I get to 5. So notice we're going to have two triangles on this one. I'll call this one triangle A and this one triangle B. So to get A, it's just going to be 1/2 the base. The base will be 2. And then the height will be what's happening at 1. So if I plug 1 into this absolute value, I will get an answer of 2. So that integral, that area will be 2. And then for B, once again, 1/2. My base is again 2. And then my height is occurring at 5, so if I plug 5 into this absolute value, I once again get 2, and that area is also 2, so if I add those two areas together, I will get 4. Okay, number 13, find the limit as x approaches infinity of 2x minus 5 times 3 minus x, all over x minus 1 times x squared plus 3. All right, as we are finding x approaching infinity, what we want to do is to find an end behavior model. So the first thing that we want to do is FOIL this out, and if I do that, I get 6x minus 2x squared minus 15 plus 5x all over x cubed plus 3x minus x squared minus 3. I could combine like terms if I want to, but mostly when we're looking for an end behavior model, we're looking for what's the highest degree in the numerator and the highest degree in the denominator. So it's going to be this term and this term. So I'll get negative 2x squared over x cubed. And the end behavior model, if I reduced that, would be negative 2 over x. So now what I want to do is to find the limit as x approaches infinity of negative 2 over x. So as I keep plugging in larger and larger numbers for x, this fraction will approach 0. So my limit as x approaches infinity would be 0. Okay, number 14, if f of x equals the sine of 2x, then f prime of pi over 8 equals what? So this is asking me to find a derivative. I am going to do a u substitution on this one. We're going to let u equal 2x, which would mean du is going to equal 2. So the derivative of sine of u is going to be the cosine of u times my du, and my du is going to be 2. So now if I just rewrite this, I like to put the 2 up front, 2 cosine of 2x, and now we're just going to evaluate it at pi over 8. So if I plug in pi over 8, I'm going to have 2 cosine, 2 times pi over 8, which will give me 2 cosine, 2 times pi over 8 would be pi over 4. And I know that the cosine of pi over 4 is square root of 2 over 2. The 2's are going to cancel, so I am just going to be left with the square root of 2. Okay, number 15, the graph of f is shown on the interval from negative 4 to 5, and it tells you that p of x is equal to the integral of f, and this is a picture of f. And it tells us to find p of negative 2, p prime of 3, p double prime of 4. So I'm just going to do a little work up here to start with. I know that p is actually equal to the integral, which is equal to the area under the curve. Okay, p prime, that derivative and the integral undo each other, so I would just be left with f, which is the curve, and p double prime would be f prime, which is going to be the slope. So I like to do that work ahead of time. Okay, p of negative 2, we're going to put negative 2 in for that x. So I'm going to be finding the integral from 1 to negative 2 of f, which we're not allowed to do because I can't go from 1 to negative 2. So I'm going to go negative 2 to 1 of f, which means I'm going to go from negative 2 till I get to 1. So I notice that I have a quarter circle and a triangle. So my quarter circle is going to be 1/4 times pi times the radius, which is 1 squared. And then I'm going to put minus because this is below the x-axis. So that triangle is going to be 1/2 times the base, which is 2, times the height, which is also 2. So if I figure that out, oh, I forgot to put a negative on this. That's going to be the opposite when we're done. I'm going to get pi over 4 minus 2. Okay, but it's equal to the opposite of that. So it's going to be negative pi over 4 plus 2. So that would be p of negative 2. All right, I'm going to go up here for p prime of 3. P prime of 3 is just the curve. So I look at 3. My y value on this curve is 4. So that answer is just 4. And then p double prime of 4 would be the slopes at 4. So if I go to 4, I notice it is on a line, and so I just need to find the slope of that line. So I'll do 1 minus 4 over 5 minus 3. That gives me negative 3 halves. So p double prime of 4 would be negative 3 halves. Okay, part B, find the x-coordinates of all relative minimums of p on the interval. So if we want to find relative minimums, we need a p prime chart. And we know that p prime is just the curve, so we're going to be looking above and below the x-axis. So I am above the x-axis till I get to negative 3, and then I stay above till I get to negative 1, and then I drop below until I get to 1, and then I'm above for the rest of it. So if I'm looking for a relative minimum, I'm looking for where p prime would change to negative to positive, which would just be at x equals 1. So when it said coordinates of all relative minimums, that would occur at x equals 1. And my reasoning would be because p prime changes from negative to positive. All right, and then find where p is concave down. Concavity has to do with the second derivative. So p double prime we've already established is looking at the slopes. So if I look at the slopes, my slopes are negative till I get to negative 2. Then they're positive till I get to, oh, that was negative 3. Positive till I get to negative 2. And then they're negative all the way till I get to 0. However, I'm going to split it at negative 1 because there's a sharp turn there, and we know that you can't take the derivative at a sharp turn. So we're going to have it's negative and then negative once again. And then my slopes are positive till I get to 3. And then my slopes are once again negative. All right, so when I want to know where concave down, here, 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 here. So that would be from negative 4 to negative 3, from negative 2 to negative 1, from negative 1 to 0, and from 3 to 5. And that is because p double prime is negative. Okay, please notice, although the picture was of f, all of these questions were asking about p, so all of my responses included p instead of f when I did those.